No. Okay, we're going to continue the memory scheduling for a while, and then we'll switch to other techniques. This is trying to solve the scheduling in a heterogeneous CPU-GPU system. Just a very brief summary. Basically, if you have a CPU and GPU together, these require memory schedulers with large request buffers. And if you have a monolithic application-aware scheduler today, this is hard to scale to large request buffer sizes. And the solution I'll describe is basically staging the memory scheduler, as the title says, right? It decomposes the memory controller into 3 simple stages. One is batch formation, which maintains row buffer locality. The other is batch scheduler, which reduces interference between applications. And the last one is a simple DRAM command scheduler, which issues requests to DRAM with FIFO queues. And I'll show you that this is actually significantly simpler and more scalable than the previous schedulers that I've described, and also provides higher system performance in a heterogeneous system. And all of the reason is these 3 stages separately are much simpler than a single stage. Okay, so let's take a look at why the problem happens. Well, this you know already. Main memory is a bottleneck. If you have many different cores, they contend for the memory scheduler. And the memory scheduler's job is to schedule those requests, right? And with different cores, you have some mix of some balance, right, in the system. How does a memory scheduler deliver good performance and fairness? There are 3 principles of memory scheduling that we're going to target here. It's not comprehensive fully yet, but one is to prioritize row buffer hit requests, right? That's the goal, to maximize memory bandwidth. This is especially true in a GPU system. In a GPU, you have lots of workloads that have very high row buffer locality, and you would like to maximize this. And we've talked about sub-array level parallelism in DRAM, right, which enabled a lot of row buffers. That's also very effective in a GPU-based system. And you know the principle. The second principle that we've developed previously is we would like to prioritize latency-sensitive applications to maximize system throughput. So we would like to still do that somehow, and we would like to be fair to everything else. And you know the principle over here. If an application has low intensity, you prioritize it. That's a simplification, of course, right? And third principle is we'd like to ensure no application is starved. This to minimize unfairness, right? So let's take a look at our motivation. How does memory scheduling change in a CPU-GPU system? GPU shares the main memory with the CPU cores. In fact, GPU is expected to share other things with the CPU cores, right? You would like to share perhaps the caches with the CPU cores, so that you can have much lower latency and higher bandwidth communication between the CPU and GPU. And it turns out GPU is much more memory intensive than a CPU. This is actually 4 times to 20 times, even more memory intensive than the CPU. Then the question is, how should memory scheduling be done when GPU is integrated on chip? If you introduce the GPU into the system with an existing scheduler, this is what happens. You have lots of requests from the GPU that occupies these buffers and floods these buffers. And as a result, a core that's perhaps latency sensitive cannot even inject into these buffers, right? Because there is no space left. This limits the memory controller's visibility of the CPU application's memory behavior and can lead to a poor scheduling decision. And the paper discusses a lot more. So a naive solution is to increase the size of the buffers, right? Make them huge. And this way you'll have something like this. The GPU will still occupy a lot, but now this core that couldn't inject before can inject. But there are problems with this large monolithic buffer. This could potentially solve the problem, and actually it doesn't solve it fully because you may want some other algorithms too. But a large buffer requires more complicated logic to analyze memory requests, right? How do you figure out what a row buffer hits? You have content addressable memory, right? You search. A naive implementation of row hit first scheduling is to search the request buffer for those requests that match the row IDs, row addresses, right? And that search becomes more complicated. To analyze application characteristics becomes harder also with many requests because you need to keep track of metadata on a request basis. And assigning and enforcing priorities to each request becomes also more complicated. You have a bigger priority encoder decoder, right? So this leads to high complexity, high power, and large die area with a large monolithic buffer. So we'd like to, as a result, you have a more complex memory scheduler over here also. So our goal is to design a memory scheduler that is scalable to accommodate a large number of requests. It's easy to implement, hopefully, It's application aware still. We would like to keep application or thread aware. And you know the benefits of this very well now. It's also able to provide high performance and fairness, especially in these heterogeneous systems. This is based on this, so the scheduler is based on several observations. And the key functions of a memory controller is threefolds. First, it should maximize row buffer hits, especially on a GPU-based system, to maximize memory bandwidth. It should manage contention between different applications to maximize system throughput and fairness, and we've looked at this quite a bit. It should also satisfy DRAM timing constraints. Remember, this is a fundamental thing to do. And current memory controllers do all of these at the same time with a single monolithic buffer, right? It has a centralized memory controller design to accomplish all three goals. We're going to decompose these into three different stages. If you have a centralized design, then it becomes complex, especially with large request buffers. So the key idea is basically to decouple these three functional tasks into three stages. Now you can come up with another functional task and you could decouple that too perhaps, but I'm not going to discuss that. You can actually extend this work in many different ways. Basically, by decoupling the functional tasks, by partitioning them into hardware structures, each of those hardware structures can be simple, and they can be collectively simpler than a monolithic scheduler also. So how do we do that? Let's take a look at this. First, how do you maximize row buffer hits? That'll be done in stage 1, which we call the batch formation stage. Within each application, the scheduler will group requests to the same row into batches. And now the rest of the scheduler will operate in the granularity of batches over here. So the batches will be sent to the second stage. It's called the batch scheduler. This is a different batch from what I've talked about in parallelism or batch scheduling, right? A batch in this case is a group of requests that hit in the same row, that go to the same row. These batches will, and the second scheduler will pick a batch from each different application to schedule from. I'll show you this pictorially. And the last stage is basically the DRAM command scheduler. Its job is to issue a request from the already scheduled order to each bank. So these parts will determine the order of scheduling, and these will be basically FIFOs that enforce DRAM timing constraints. So hopefully this is the simplest part. So let's take a look at these three things in a little bit detail. And if you're interested in this, I think extending this work in many different areas is possible, especially to an even more heterogeneous system. You can consider other accelerators also. So what does stage memory scheduling look like? Basically, we want to get rid of this huge request buffer. We want to do something like this. We have stage 1 that forms the batches, stage 2 that schedules the formed batches, and stage 3 that consists of FIFOs for each bank that just does DRAM command scheduling. So what does stage 1 do? The goal here is to maximize row buffer hits. At each core, we want to batch requests that access the same row within a limited time window. Right? A batch is ready to be scheduled under two conditions. First, when the next request accesses a different row, then you complete the batch. And the second, when the time window for the batch formation expires, so that you don't wait for a request to be batched. And we're going to keep the stage simple by using per core FIFOs. Let's take a look at this. Basically, we have a FIFO queue for each core. And cores inject requests from their last level caches, or maybe perhaps a shared last level cache into this FIFO queues, into their FIFO queue. And this leads to stage 2, batch scheduling. Let's say core 2 sends a request to row B and keeps sending some requests to row B. When a request to row C comes, we form the batch. We say that you have a batch of 2 requests, group of 2 requests. Core 1 injects requests to row A, and after a while, it stops injecting requests, and the scheduler says, oh, we've already injected, it's been so much time since we injected the last request, and the time window expires, and a batch is formed. That way, you can form multiple batches, and cores can form many batches. And these batches can be of varying sizes, as you can see. Right? And GPU batch is actually going to be much larger, because GPU injects lots of requests. So that's the idea. Group requests that go to the same row separately from each core. Now, one downside, as you see here, is what happens if core 2 injects a request to row B over here, right? That's not batched with this algorithm. And we're going to lose some performance because of that. But that increases complexity. If you want to merge that request that goes to row B after a request to row C, you need to do this content addressable search somehow. And we want to minimize that. The paper discusses what happens if you actually do that merging You get better performance at the cost of more complexity. So what does the batch scheduler do? Once you have these batches from different cores that go to different rows. The goal of the batch scheduler is to minimize interference between applications. Basically, it's there to manage the contention, inter-application contention. Stage 1 already forms batches within each application. Stage 2 schedules these batches, larger granularity requests from different applications. And it schedules the oldest batch from each application, so it's not out of order. It takes the head of the head batch. That makes the stage 1 simpler. Then the key question is, which application's batch should be scheduled next? Which one do you pick? Again, the goal is the same as before, to maximize system performance and fairness at the same time. And to achieve this goal, the batch scheduler chooses between two different policies. So we're going to have two different policies, and we're going to pick which one to choose from, and we're going to randomize that choice. So this is a different algorithm, and I think going forward, randomized scheduling algorithms or randomized resource management algorithms will become much, much more interesting, since systems are scaling not very easily if you don't have if you try to cluster things. So that's one of the downsides of clustering. It's not robust, whereas if you have a randomized algorithm, it's usually much more robust. So let's take a look at two scheduling algorithms. You could actually have more, but we've decided to design two algorithms. One is shortest job first. This might sound familiar. Basically prioritize the applications with the fewest outstanding memory requests because they make fast forward progress, right? This is very similar to Atlas's insight and insight we had with thread cluster memory scheduling. The upside, it gets good system performance and somewhat good fairness, at least with when the GPU is around. The con is, the downside is, it's actually not as good for starvation. Basically, the GPU and memory intensive applications get deprioritized in this case. So this is the same trade-off that we've seen. On the other hand, actually this fairness should not be fully there because this is actually a fairness con, right? On the other hand, the other algorithm that we will employ is round robin. Remember we had two opposite extremes, throughput oriented versus fairness oriented. The fairness oriented one will be more round robin. This prioritizes the application in a round robin manner to ensure that memory intensive applications can make progress. The upside, GPU and memory intensive applications are treated fairly with round robin, if you remember, and GPU is important here. The downside, GPU and memory intensive applications significantly slow down others. So if the GPU is important, then you would like to pick this one. If the GPU is not important, then you would like to pick perhaps this one for a while. So our scheduling policy, the importance of GPU determines the scheduling policy. Scheduling policy needs to adapt to this. So we have a hybrid policy that every cycle, again the granularity can change here and we've explored the granularity. With probability P, we pick shortest job first. And usually this benefits the CPU because CPU jobs, CPU batches are short, or threads have less memory intensity. Right? With probability 1 minus P, we pick the round robin scheduler. This benefits the GPU because GPU has lots of requests. And round robin between batches, right? Not round robin between cores. GPU has large batches, and when you get to this round robin, it can inject lots of requests into the system. And system software can actually configure P, or we can dynamically adapt P. We didn't explore the dynamic adaptation yet, which is a very interesting direction again. But system software can configure this P based on the importance of the, or weight of the GPU. If the GPU is more important, you can have a lower P value. And I'm going to show you results with different P values. So once you pick the batch with the policy, that batch gets injected to the next stage, right? And a batch, by definition, goes to the same bank because these are requests that go to the same row. So let's say a GPU has 20 requests. Its 20 requests get injected to the bank that they're destined to. The last stage is the DRAM command scheduler. And this is going to be simple because high-level policy and scheduling decisions, ordering decisions, have already been done by the first two stages. Stage 1 maintains robot for locality. Stage 2 minimizes inter-application interference. There's no need for further scheduling here, so we're going to keep it simple. Its goal is to service requests while satisfying the DRAM timing constraints. And you remember the DRAM timing constraints, there are many. So we implement this as simple per bank FIFO queues. And I guess that's it, basically. There's no scheduling here. Let's put everything together. Basically, in stage 1, we form batches. So you have batches of different sizes from different cores and batches that are usually large from the GPU. Stage 2 basically picks between those batches. and stage 3 has simple FIFO queues. If the current batch scheduling policy is shortest job first, stage 2 picks this core because that looks like the shortest job, right? And that shortest job first is within a time interval. With some probability, the next cycle, the scheduling policy switches to round robin. If that's the case, then we do scheduling in a round robin order across these queues. And if it's round robin, you keep scheduling in the round robin order. And this stage basically takes these requests and schedules them to the bank. It's simple, right? Every stage is much more simple than doing everything at once with a monolithic scheduler. So what's the complexity of this? Basically, we've implemented SMS, this is called stage memory scheduling, SMS, on a Verilog model, and we have actually newer models also, but it doesn't matter. The results are very consistent. Stage memory scheduling compared to a row hit first scheduler, which is not application aware, consumes 66% less area and 46% less static power and less dynamic power, which I don't have the result for here. And this is compared to a row hit first scheduler. If you have an application aware scheduler like thread cluster memory scheduling, this is much simpler. And the reduction comes from several reasons. First, the monolithic scheduler leads to a stage of simpler schedulers. That's the main reason. And there are 3 components of this. Each stage is a simpler scheduler because it considers fewer properties at a time, right? The top stage, stage 1, considers only row buffer hit rate. The second stage considers how big the job is and the probabilities. And the third stage considers just the timing constraints instead of considering all of them at the same time. Each stage has simpler buffers. They're FIFO. All of the buffers are actually FIFOs instead of out of order schedulers. And each stage has a portion of the total buffer size instead of the entire monolithic buffer size. Buffering is basically distributed across these stages. Any questions before I move on to the results? Okay. So let's take a look at some results. It turns out actually methodology is very difficult in this area if you have CPU and GPU together, because it's not clear what kind of workloads you would put in this, and also it's not clear. It's not easy to simulate also. So what we've done is we have 16 out of order CPU cores and 1 GPU modeling based on AMD's Radeon system, and this is our DRAM model. And we have a bunch of workloads, some GPU traces obtained from AMD that have recent games and some GPU benchmarks, and CPU workloads will be spec workloads. So there's sharing of memory, but not a whole lot of communication. So communication would make this even more interesting going forward. And there are a bunch of workload categories based on the memory intensity of the CPU applications. And you can read the paper for more detail. Let's take a look at a qualitative comparison to previous scheduling algorithms. You know already that row hit first scheduler is not good for multi-core. Atlas scheduler leads to low fairness, you know that. And thread cluster memory scheduler, which is the closest work to what we have here, has good multi-core performance and fairness, but it's not robust. We found that it misclassifies latency sensitive applications when you have a GPU that's very different from everything else in the system. So if you have this, and if you have a clustering algorithm that clusters applications to latency sensitive and bandwidth sensitive, a lot of the CPU applications become latency sensitive and they're treated very similarly, because GPU floods the system. And we actually tried to fix that problem, but it seems like it's a tough problem to fix. Evaluation metrics is another issue actually in this case. Basically, how do you actually evaluate the performance of a system like this? For CPUs, normally in a multi-program workload, this is the metric. Basically, you have a weighted speed up. For each application, you get the IPC of the application when it's running together, whether there's divided by IPC of the application when it's running alone, and you sum them up. How do you do that for GPU? GPU's performance metric is frame rate speed up. In our case, basically we look at the frame rate shared when it's running together with other cores, and frame rate alone when it's running alone. So that's kind of GPU's speed up. So how do you actually combine this? It turns out to be not easy, so we actually introduced a metric called weight, GPU weight. And this is the CPU and GPU weighted speed up. And you may want to optimize this entire thing. You may want to optimize for a given GPU weight. The GPU weight may be 0, for example. In that case, you care only about the CPU. The GPU weight may be infinite or high enough. In that case, you don't care about the CPU as much. And I'm going to give you results for a variety of GPU weights. we've looked at several system scenarios, a CPU-focused system and a GPU-focused system. Let's take a look at the CPU-focused one. Here, the GPU weight will be low, which is 1 in this case. It's not that low, but it's still low. So we configure stage memory scheduler such that the P, the probability of choosing shortest job first policy, is high, such that CPU is prioritized, 0.9. So this mostly uses the shortest job first batch scheduling policy. As a result, you prioritize the CPU. This is the performance that you get across different workload categories. This is y-axis is the CPU, GPU weighted speed up, entire system performance. And if you look at the performance, I'm not going to go into detail again. You see that SMS provides the best performance compared to all previous scheduling policies. In fact, we looked at other scheduling policies also. And this is true for most categories except for the high intensity category, where SMS's decisions are not robust also. Basically, this allows latency sensitive applications to get serviced as fast as possible. And the best scheduling policy turns out to be Atlas because TCM is not very robust for a GPU-based system. And it's on top of this, SMS is much less complex than previous schedulers. If you look at a GPU-focused system, we give a high weight to GPU such that it's more important. And we set the probability of shortest job first selection to 0, such that we always do round robin, basically across these queues. And this prioritizes the memory-intensive applications. But it does also give some chance to the CPU cores to inject requests, right? And the performance of this looks like this. Basically, you schedule GPU requests more frequently, and the performance improvement is little over row hit first scheduling. Because it turns out row hit first scheduling is very nice for a GPU. Because GPU has streaming workloads, and if you do row hit first scheduling, all of the requests will hit in the row buffer. Actually, a lot of the requests will hit in the row buffer. But if you look at this actually, the other workloads, the other schedulers, Atlas and TCM, which are application aware, which are supposed to be better, don't do too well in a GPU-focused system, right? It's actually, the reason is memory bandwidth is extremely precious in a GPU, in a system where you care about the GPU. Because GPU's performance is very much affected by the memory bandwidth, streaming memory bandwidth. Anything that reduces row buffer locality hurts the performance of the GPU. And these Atlas and TCM obviously reduce row buffer locality, right? Atlas, for example, you would prioritize an application that's less intensive than the GPU over the GPU. As a result, GPU's row buffer locality gets destroyed significantly and GPU gets delayed significantly. Similarly, in TCM, you prioritize some other application that has low row buffer locality over the GPU. So this indicates that you should treat a GPU-based system very differently than a pure multi-core system that's CPU-based. Okay, this is also true. So we've also varied this GPU weight from this value all the way to 1,000. This is where GPU is not important, GPU is very important, and this is system performance. And this is the curve you get with the best previous scheduler. And best previous scheduler varies actually. If the GPU is not that important, Atlas is the best scheduler. And this makes sense, right, for system performance, because Atlas prioritizes lower intensity applications. For a place where it's not clear, thread cluster memory scheduling is the best previous scheduler. And this may be an important part of the space, even though it looks small. For other space parts where GPU is very, very important, then row hit first scheduling becomes the best previous policy. So what does SMS do compared to this? If you look at SMS's performance, SMS is actually still the best scheduler across all GPU weights, it turns out, except its performance improvement is not as high over here. When the system is GPU focused, its performance improvement is not as high. When the system is more CPU focused, it provides much higher performance. There are some additional results in the paper that I will not go into. So fairness also improves here. And you can actually adapt to different fairness, and you can get individual CPU and GPU performance breakdowns. And then once you design a scheduler like this, then the question is, can you actually apply this to multi-core only, right? It turns out if you do this for just a multi-core system, you get competitive performance with previous algorithms. So you get very close to thread cluster memory scheduling, but not as good. You get within 4% of thread cluster memory scheduling. It turns out the performance and fairness of the scales better than previous algorithms as the number of cores and memory channels increases, because it's more graceful in terms of how the queue behaves. And you can look at the paper for design parameters also. I guess I'll conclude this quickly. Basically, I've told you all of this. Heterogeneous CPU, GPU systems require memory schedulers with large request buffers, and treatment of GPU needs to be different. As I've shown you, application-aware memory schedulers do not do too well if the GPU is very important in the system. In existing monolithic applications where schedulers are hard to scale to large request buffer sizes. The solution that we've looked at is staged memory scheduling that decomposes the memory controller into 3 simple stages based on the functional tasks. One is to maintain row buffer locality. We have a batch formation stage which feeds into the batch scheduler, which reduces interference between different applications, and which has a probabilistic scheduling policy. It picks between different scheduling policies in a probabilistic manner. And I think going forward, that probabilistic manner will become much more important in systems. And DRAM command scheduler gets the request from the batch scheduler, and it simply issues requests to DRAM taking into account timing constraints. As a result, you get a decomposed scheduler that's significantly simpler and more scalable than state-of-the-art schedulers. And it also provides higher system performance and fairness. Any questions? Is this interesting? I think going forward, this is actually a very interesting topic. How do you do better than this for a CPU and GPU-based system? And how do you actually employ some of these ideas in a multi-core system? And what happens with more levels of heterogeneity, right? What happens if you have other types of cores that are injecting into this request buffer? Okay, I'll switch gears a little bit. I've talked a little bit about this, but none of these previous schedulers, if you look at them, they don't provide strong memory service guarantees, right? Basically, if your goal is to satisfy performance bounds and requirements in the presence of shared resources, and maybe all of these things, you may want strong memory service guarantees. Basically, the approach to get strong memory service guarantees that we will take is to develop techniques and models to accurately estimate the performance of an application in the presence of resource sharing. In this case, our resource will be main memory. And develop mechanisms to enable the resource partitioning and prioritization needed to achieve the required performance level. So, for example, you can estimate the slowdown of different applications with a model, and I'll tell you one model to do that. You can feed those slowdowns to the memory scheduler such that the memory scheduler achieves the slowdown goal of each different application. And we're going to try to do that also. Of course, we're going to try to do this all the while providing high system performance. If this is not your goal, again, it's very easy to solve this problem. You can easily get a strong memory service guarantee by underutilizing your system. But that's not what you want, right? Otherwise, why are you designing these scalable systems in the first place? I'll talk about the latest work that I've alluded to. This is called MICE, Memory Interference Induced Slowdown Estimation. I'm going to skip some of these. Basically, we're going to try to solve the problem of unpredictable application slowdown. You have this Leslie 3D application running with GCC having some slowdown. And if it's running with MCF, it's having some other slowdown, right? And we've seen this. An application's performance depends on which application it's running with. We're going to try to make it more predictable. Why is this important? Well, when multiple applications share resources, especially if some applications require performance guarantees, you would like to have this. Let me fix something. PowerPoint decided to have a mind of its own, I think. There you go. That must be a PowerPoint bug also. Too many bugs. Okay. It's doing something. Okay, so there are many examples actually. I'll just give 2 examples. In mobile systems, for example, you can be running interactive applications with non-interactive applications in multi-core. And you need to guarantee performance of these interactive applications. Second thing is in server systems, when you're running a cloud computer system with different servers, jobs consolidated on the same server, you need to provide bounded slowdowns to critical jobs, to those jobs that require performance guarantees. So our goal is to provide this predictable performance in the presence of the memory interference. How do we do that? As I told you, we would like to estimate the slowdowns of applications and control the slowdowns of the applications. Let me first talk about some key observations. It looks like you cannot see anything here, but there is stuff here. But they'll become apparent later on, unfortunately. The first thing is key observations, and then we'll go into implementation. well, you know the slowdown definition. It's performance alone divided by performance shared, right? So the first observation that Lavanya has made is, for a memory-bound application, performance correlates with memory request service rate. These are results from a real system from Intel Core i7 with 4 cores with a large memory bandwidth. And x-axis is the request service rate given to a particular application, in this case Omnet PP. 1 means you don't limit the request service rate it gets. It gets the full bandwidth. 0.5 means there's an application running with it that's consuming 50% of the memory bandwidth. We write a micro benchmark that consumes exactly 50%, and this gets only 50% of the memory bandwidth. And you can actually write a configurable workload that becomes a memory hog and doesn't give that fraction of the memory bandwidth to this application in question. And on the y-axis, we see normalized performance. So you see a linear relationship. As you give more bandwidth to the application, as you increase its request service rate, its performance improves linearly. And this is a memory-bound application. That's why this works. And this is true for other memory-bound applications on a real system and also on simulation. Performance correlates with memory request service rate. That's the first observation. If you look at slowdown, slowdown is performance alone divided by performance shared, right? Performance you have when you're running alone in the system, performance you have when you're sharing resource main memory with the other applications. If you have this observation, then slowdown can be estimated by just looking at request service rates, right? Request service rate alone divided by request service rate shared. So that will be our performance model. And the key question is, well, the easy part is request service rate shared is easy to get, right? Basically, when the application is running with other applications, you know how many memory requests it's sending in a given time interval. And that's the request service rate, or getting serviced. Whereas this one is harder. How do you get the request service rate alone of an application when it's running together with other applications? And this is the request service rate when it's running alone. That's where key observation 2 comes in. This observation says request service rate alone of an application can be estimated by giving the application highest priority in accessing memory. So you change the memory scheduler, give that application the highest priority for a while. In that case, it looks as if the application is running alone. Because it gets the highest priority, it has little interference from everybody else. Now that's almost as if the application were run alone, but it's not perfect because there are row buffer issues and there are some other issues that I'll tell you about. So when the application is run, let me give you this pictorially. When the application is run alone, this is the request buffer state and it's the service order. So it gets these 2 requests serviced in 2 bank access latencies. When it's run together with another application interferes with this. And if you look at this, it's last request gets serviced after 3 bank access latencies, so it gets interference. When the application is run with another application and it gets highest priority, then the memory scheduler prioritizes these red requests over the blue one, and its request services look like this, and its service time is very similar to as if it were run alone. Right? That's what we're going to try to exploit. So for the memory-bound applications, this is our performance model, slowdown model. Slowdown is request service rate alone divided by request service rate shared. And this is estimated by giving the application highest priority when accessing memory. This makes sense so far, right? Okay, so this is nice for a memory-bound application because a memory-bound application is actually dominated by the time it spends on memory. Right? It has a small amount of compute phase, and if you look at that, it has some memory phase over here. When it's interfered with by another application, this is what happens. Its requests take longer, right? And its memory phase gets longer, but its compute phase is very small. As a result, this memory phase slowdown dominates overall slowdown. So you can do request service rate alone divided by request service rate shared, right? But if you have a non-memory bound application, then it becomes a little bit different, right? It basically alternates between long compute phases and short memory phases. And as you get interference, what happens is the memory phases become larger. But still the application is dominated by the compute phases. So we're going to introduce this alpha value that denotes this memory phase. And request service rate actually affects only the memory phase, right? It doesn't affect this part, the compute phase. So we have 1 minus alpha over here that denotes the compute phase, the fraction of the compute phase. And with interference, this 1 minus alpha part doesn't change, but this alpha part gets scaled by the request service rate, slowdown. It's only the memory part that really slows down with interference, right? The compute part doesn't slow down with interference. That's the key realization. And now we have a performance model for actually general all applications. This is the slowdown you get. 1 minus alpha, which is the compute phase fraction, plus alpha, which is the memory phase fraction, times request service rate alone divided by request service rate shared. That's the final slowdown model for all applications. Oh, these appeared now. Interesting. I don't know how that happened, but
We observed.
yeah, I'm not going to complain that it happened.
After we observed, it becomes...
I see. Yeah, interesting. Maybe after we observe. So now that we have the key observations, how do we implement something like this? We're going to operate based on intervals. There are actually better mechanisms to do this, but intervals are simple. Right? Within an interval, the memory controller will measure request service rate shared, which is easy, and alpha, which is also easy because you can figure out how often the application spends time on memory. Basically, this is the memory episode fraction. And it estimates request service rate alone. Right? This is, and you do this by prioritizing the application in the memory scheduler. It estimates the slowdown at the end. And in the next interval, it does the same thing. And in the next interval, it adapts its scheduling policy to do something else. But we'll talk about that later. Let's take a look at how we measure request service rate shared and alpha. As I said, this is easy. You can have a per core counter to track the number of requests that are serviced. At the end of each interval, we measure the number of requests serviced divided by the length of the interval. Basically, requests per second, for example. Memory phase fraction is also easy. Basically, we can count the number of stall cycles at the core. How often is the core stalling? Or compute, and then we can compute the fraction of cycles stalled for memory. Right? That's also easy. Basically, this is stall cycles divided by interval length. This is the harder part. The goal is to estimate request service rate alone. And the memory controller periodically gives each application the highest priority in accessing memory to be able to estimate this. So how do we do this? We divide each interval into shorter epochs. At the beginning of each epoch, memory controller randomly picks an application as the highest priority application. At the end of an interval, for each application, it estimates this number of requests during these high priority epochs divided by number of cycles applications given high priority. Now, it turns out if you do this, it's not that accurate because there's something, memory scheduling is not preemptive. When an application has highest priority, it still experiences some interference. And there are several reasons for this, but we're going to tackle one important reason, which is the memory scheduler being non-preemptive. So let's say you have this application again that has high priority, and it has this request that is serviced, and you have this blue application that generates a request. After this, its request starts being serviced. While it's being serviced, another request from the red application comes in. But because memory scheduling is not preemptive, it basically first finishes this request and then schedules the request of the red application. And this happens even if you give the red application the high priority, right? If another request comes from the blue application in between two requests of a red application, the memory controller starts servicing the blue application because it's work conserving. You don't want to waste bandwidth during that time. But if you do this, if you're non-preemptive about it, this blue request causes interference to the red request, right? Even though the red application has high priority. Now, you could solve this problem by making the memory scheduler preemptive, but that incurs a lot of overhead in terms of the DRAM timing. Right? So we're not going to do that, but we're going to compute these interference cycles somehow. Basically, that's the solution. Determine and remove interference cycles from request service rate alone calculation. And this is what we do. Request service rate alone is computed as number of requests during high priority epochs divided by number of cycles the application is giving high priority minus the interference cycles. Interference cycles is if an application is high priority and it's accessing a bank, but the memory controller is servicing some other application's request in that bank, you increment a counter that says it's interference. Well, I already told you that. Okay. Let's put it all together. So I've actually given you the entire model. Basically, it's an interval-based model. that measures request service rate shared alpha, request service rate shared and alpha, and it estimates request service rate alone as I described. There are still inaccuracies here. Row buffer is another inaccuracy, but we're going to keep it simple right now. So how do we evaluate the model? We want to first estimate how accurate are these slowdown estimations. There are a bunch of works on slowdown estimation. The first one is what I've described to you earlier, stall time fair memory scheduling, that estimates the slowdown in main memory. This I will describe to you later. Fairness via source slotting also uses mechanisms from stall time fair memory scheduling, but except it estimates the slowdown in the entire chip. Per thread cycle accounting is a recent one that has similar principles to stall time fair memory scheduling. But I'm going to focus on stall time fair memory scheduling. Remember, the basic idea was memory controller estimates the slowdown as stall time, memory stall time of the thread alone divided by memory stall time of the thread shared. This was easy, and this was hard, as usual. And for stall time memory scheduling, what we did was we counted the number of cycles an application receives interference. The major advantage of mice over STFM is STFM estimates performance while an application is receiving interference. It turns out this is very hard. Here with mice, the key observation is that if you give the application the highest priority when it's sharing a main memory with others, it is a lot easier to estimate this stall time alone or request service rate alone. Before, remember, with STFM, we were trying to estimate stall time alone while the application is being deprioritized. And it turns out this is tough. So we would like to give high priority. That's the first advantage. The second advantage is stall time fair memory scheduling does not take into account the compute phase. That alpha is not a factor in stall time fair memory scheduling, whereas mice accounts for that compute phase. As a result, it gets better accuracy. I'm going through this relatively quickly, but if you're interested, feel free to stop me. So we look at, again, a system similar to what we've examined before. We have 300 multi-programmed workloads, and I'll give you results as to the accuracy of the model. And these results hold with a variety of parameters, with different parameters also. This is the slowdown of a spec CPU 2006 application, Leslie 3D, running together with 3 other applications on different cores. And this is time on the x-axis, slowdown on the y-axis. And I'm going to show you the actual slowdown first. And this is the predicted slowdown by stall time fair memory scheduling, so it's way inaccurate. And this is the predicted slowdown with mice. So the accuracy is a lot higher. It tracks the slowdowns that are actual. And this is true for many applications that we've examined. These are the applications that are memory intensive, and these are not memory intensive. If you look at these are actual slowdowns. These are the predictions from stall time fair memory scheduling. So the predictions are still off, even if the application is memory intensive. If the application is memory non-intensive, the predictions are even more off because we don't take into account the compute phase in stall time fair memory scheduling. And these are the predictions that you get with mice. So for almost all applications, the prediction, the tracking of the real slowdown is usually accurate. Now this looks a little bit upsetting. This goes up, this goes down, but it's not that big of a variance, as you see. So the average error of mice across all these workloads is approximately 8%, whereas the average error of STFM is approximately 29%. So that's how we reduce the error. 8%, the error is due to all of these other effects, right? Row buffer locality that we do not take into account. There's interference in the row buffer. There's interference in bank parallelism that we do not take into account. There's interference in other effects like writes versus reads. There could be writes that are happening because of interference that wouldn't have happened. If you take all of those into account, then you can reduce this error probably to much lower, but then the system becomes a lot more complex, right? So this seems like a reasonable trade-off at this point. So now that you have a reasonable slowdown estimate model, what do you do with it? Right. Actually, I'll talk about just one in a little bit detail, but you can imagine many different policies, right? You could actually do stall time fair memory scheduling based on this, right? The scheduling policy of stall time fair memory scheduling, you could use the slowdown estimate model. We'd like to provide soft slowdown guarantees. our goal is to ensure a quality of service critical application meets a prescribed slowdown bound. And the second goal is to maximize system performance for all other applications. The basic idea is to allocate just enough bandwidth to the quality of service critical application and assign the remaining bandwidth to other applications. Just enough means enough bandwidth such that the quality of service critical application doesn't fall short of its slowdown goal. So what is the mechanism for this? Basically, we assign initial bandwidth allocation to the quality of service critical application and estimate the slowdown. This is what the memory controller does. It estimates the slowdown of quality of service critical application using this mice model that I've discussed. And after every n intervals, it checks if the slowdown is greater than the bound plus or minus some epsilon to enable hysteresis. It increases the bandwidth allocation because slowdown is much higher than the bound in this case. The application is slowed down too much. If the slowdown is less than a bound, then it decreases the bandwidth allocation because it's meeting these slowdown guarantees nicely. You could actually imagine other policies. This is a simple one to implement. When slowdown is not met for n intervals, then the scheduler notifies the operating system so that it can migrate or deschedule jobs. Basically, the scheduler gives up in this case, saying that I cannot meet the slowdown. Let's evaluate this. Basically, we have each application, among the 25 applications in total that we have, considered to be the quality of service critical application. And we run each of these applications with 12 sets of corunners of different memory intensities for a total of 300 multi-program workloads. And each workload is run with 10 slowdown bound values for the quality of service critical application. So we're going to vary that slowdown bound. We're going to look at a baseline memory scheduling mechanism. Stall time fair memory scheduling results are in the paper. I'm not going to add that here so that we don't clutter the slides. But there's a previous work that always prioritizes the quality of service application. That's the idea over there. If an application's quality of service critical, just prioritize it. And we're going to compare to that. Other applications requests are scheduled in first ready, first come, first serve order in this case. So if you look at this is overly conservative or overly aggressive, depending on how you look at it. It basically, even if the application is meeting its slowdown, it's always prioritized, right? Which means that the system performance will not be very high with this mechanism. Let's take a look at one workload. This is Leslie 3D with 3 other workloads again, and y-axis is the slowdown of the workloads. Let's assume that quality of service critical application is Leslie 3D, and these are non-quality of service critical. If you always prioritize Leslie 3D, these are the slowdowns you get. Which means that this is the best slowdown you can get with this workload mix for Leslie 3D. Right? Now, if you use mice with a quality of service bound of slowdown bound of 10, basically, if Leslie 3D should not be slowed down by more than 10, this is the performance you get. Leslie 3D meets its performance, and these applications perform much better. Right? Their slowdowns are much lower. Let's try reducing the slowdown bound. Leslie 3D's slowdown bound is 3.33 right now. Again, its slowdown meets its performance, right? It's less than 3.33. And these applications' performance is still improved, right? Compared to always prioritize. So we have a better mechanism than always prioritize because you have better system performance and you're still meeting the slowdown guarantees. Let's take a look at a bound of 2. In this case, our mechanism barely meets the performance goal, which is 2, and it improves performance in some other applications, maybe not all, but some. So you barely meet the slowdown goal and you still improve performance. If the slowdown goal is even lower, even tighter, at that point you stop meeting the slowdown goals. And we become very similar to always prioritize if you look at this. And even then there's a slight performance gain in some applications. So this is one case study, but there are a lot of workloads behave similarly. Mice is effective in meeting the slowdown bound for the quality of service critical application if that slowdown bound is meetable. And it's effective in improving performance of non-quality of service critical applications. These are 2 key conclusions. So we did a large-scale study across 3,000 data points. That was just one workload. If you look at all these 3,000 data points, 300 workloads with 10 different slowdown bounds, you can classify these data points in 2 dimensions. Mice can meet the quality of service bound or not meet the quality of service bound. And it can predict the quality of service bound can be met or is met, or it can predict that it's not met, right? That could be its estimation. Whereas if you always prioritize an application that's quality of service critical, you don't know if the slowdown bound is met or not met. Whereas with mice, remember, we can actually know. Well, I guess I have to go back too much. Yeah, when the slowdown bound is not met for n intervals, we know that that slowdown bound is not met. We cannot meet that bound. That's the prediction. So we're going to look at the accuracy of that prediction. Oh, I've gone too far. So if you look at this, for 80.9% of the workloads, mice meets the bound, the prescribed bounds. And always prioritize meets the bound for 83% of the workloads. So we're actually doing pretty well. When the float bound is meetable, we can meet it most of the time. And mice correctly predicts whether or not the bound is met for 95.7% of the workloads. So for most of the workloads, we know that we're doing the right thing or not. And in this case, always prioritize has no idea about this, right? Because you're always prioritizing without looking at slowdowns. I guess the worst part is this part, right? You meet the quality of service, you don't meet the quality of service bound, but you predict that it's actually met. This is basically a false positive, almost. And this is a false negative. You meet the quality of service bound, but you think that you haven't met the quality of, you haven't met the bound. So you lose some efficiency here, but you do the wrong thing here. So we'd like to ideally minimize this, minimize both actually. And I guess it's not too bad right now, 4.3%. Okay, so let's take a look at the effect of this on performance of non-quality of service critical applications. As you increase the slowdown bound, this is always prioritized. This is a harmonic speed up across many workloads, and this is the number of memory intensive applications. If you look at the average over here, you get higher performance on non-quality of service critical applications when the bound is loose. And this is expected, right? If the bound is loose, you're comfortably meeting the slowdown bound, and you're allocating the remaining bandwidth for non-quality of service critical applications, so we're improving system performance. And when the slowdown bound is 10/3, mice improve system performance by 10% while meeting the slowdown bound for that amount of time. Okay, so that was one policy that we've discussed. How do you provide soft slowdown guarantees? And I say soft because it's not hard deadline scheduling, right? With a hard real-time scheduling, you have hard deadlines and you need to somehow obey them. And we're not solving that problem here. We're trying to be more soft and probabilistic. Many systems do not require hard deadlines unless they're safety critical. And we're not targeting those systems here. You could also do another policy, which is minimizing maximum slowdown. And I will not talk about that. Basically, it's in the paper, but you can see that if you design a policy that's very similar to stall time fair memory scheduling, prioritize the application that has the maximum slowdown, then it improves fairness across many system configurations. And the paper actually has a lot more results, so you can take a look at that. So to summarize, uncontrolled memory interference slowdowns applications unpredictably. Our goal is to estimate and control these slowdowns in a predictable way. The key contribution is an accurate slowdown estimation model, MICE, which is an average error of 8.2% compared to a 29% error of the best previous mechanism. And the key idea is to use request service rate as a proxy for performance and estimate request service rate alone by giving the application the highest priority in accessing memory. And once you do that, you can leverage the slowdown estimates to control slowdowns. You can provide soft slowdown guarantees that I've discussed. And this way you can be accurate by about 95% in knowing whether or not you meet the bound. And you can also minimize the maximum slowdown to improve fairness. Any questions? I'm going pretty fast, so maybe I should slow down? No? Okay. Or are people getting tired? Not yet? Okay, it's almost 4:30. Well, we'll continue, I think. Okay, some current directions, I think, building upon this. Lawine is looking into building a comprehensive slowdown estimation model. how do you provide performance predictability with other shared resources also together? And I think this request service rate is a good proxy for for the entire shared resource system. In heterogeneous systems, it's also interesting. And interaction with power and energy consumption is also interesting. So we're looking at more integrated techniques, and I'll talk about some of these, so this is an early slide. Once you have the slowdown information, one other interesting direction is if you actually can accurately estimate these slowdowns, you can exploit this information in software. For example, you can expose this slowdown information such that the software does better migration, thread migration to different cores, or better admission control. If the software knows that these slowdowns are not met for a long time, basically it can decide, oh, these applications are not going well with each other, so maybe I'll not admit this application to this particular core, right? And you could actually do perhaps more better billing policies. If you're not meeting the slowdown, you don't bill the customer that much. So I think these are very interesting directions if you have a good slowdown estimation model. Okay. So far we've been looking at smart resources still. Now let's switch gears a little bit and take a look at these dumb resources approach. We've been designing over here memory controllers, not interconnects, memory controllers that are smarter and smarter, hopefully. But another approach is to keep the system simple, to keep each resource simple, but add enough mechanisms such that you keep enough information about these different resources, and based on that do injection control or data mapping. And the first solution that I'll explore is source throttling. You've seen this before, but we're going to look at source throttling to actually try to provide something similar to predictable performance, but I'll talk about it from a point of view of fairness. Do you need to change it? This may be a good place to do that.